Now let us consider the next type of problem. This problem is curve fitting. So, well, imagine that you perform experiment, right? You have different inputs, and then you measure the output, right? So you have correlation between x and y, right? You have data set which represent the correlation between input and output. Let's say that a quantity of y is known to depend on another quantity x. Y depends on x, and a set of corresponding value has been collected for x and y and is presented in this table. You see that once we set x, right, and once x change, the output change. Once input change, output change, corresponding to that one. So we see that we have a number of experiments. We have how many of it? Well, for the first table we have 10, right, set of experiment, and then we have 9 sets of another experiment, and in totally we have 19 data points, right? Correlation between input and output. Y is our output and x is our input. So you see that if we plot it in x, y, two-dimensional diagram like x and y, you see the scatter of this data, and you see that it is somewhat linearly dependent between the x and y, between input and output, right? So what we're going to do, we want to fit the best straight line. We see that x and y, y is linearly dependent on x. When x change, y also change, right? So the structure of the model is y equals bx plus a, where b is slope and a is our intercept. Okay, so the objective is to minimize the sum of absolute deviations of each observed value of y from the value of predicted by the linear relationship. Okay, then we again the first one we fit the straight line, right, and we try to minimize the sum of absolute deviation, okay, or absolute error. And the second problem is we repeat the problem again. We fit the best straight line y equals bx plus a, where the objective is to minimize the maximum deviation of all the observed values of y from the value predicted by the linear relationship. And the third problem, we want to fit the best quadratic curve y equals cx squared plus bx plus a to this set of data points using the same objective as in 1 and 2. Okay? Okay, we will work on the first problem first. Okay? Okay, we set out on our problem, the first problem. Well, we have, of course, again, I would like to explain the idea first. Yeah, we have x and y, right? We have x as an input, we have y as an output, and you have a data set from the experiment. You got many points. Of course, this just for it's not the real data from the problem. Of course, just to show you what the idea of the problem. So we want to find the it can be like this, right? Y is ax plus b, right? We have two parameters. We have a and b as a parameter. So for the first question, first problem, you see that what we want to fit the base straight line y equals bx plus a to this data set, right? And well, the objective is to minimize the sum of absolute deviation. All right, so well, we back to the data again. You see that we have a set of data. Yeah. All right, so well, you see that we have two parameters. Our decision variables are decisions variable x, a, and b, right? Because y and x are from our data set, experimental data set. And well, we have to adjust a and b in order to obtain the minimum error. Okay, minimum summation of deviation. So that means a minimum error. So what is the error? Error can be here, right? Yeah, summation of the deviation from the predicted point, predicted correlation with the experimental data. So well, you see that if we, what happened if we change a, we change a, well, that means, well, we're going to change the slope, right? The slope, yeah, the slope can be like that. You just change the slope in order to obtain the minimum point, minimum deviation, or you adjust b. That means, well, you move, because b in intercept, right? So you move that that way, yeah, by maintaining the slope, and you move it, yeah, left or right. Okay, so you see that we can adjust a and b in order to obtain the minimum minimum deviation. Okay, summation of deviation. Okay, so well, what we're going to do is to, for the first question, we want to, of course, we have to a and b as our decision variable, a and b, and we want to minimize our objective function, and the our objective function is the, yeah, summation of deviation. So this is interesting because, well, you see that error can be both negative or positive, right? So well, you cannot just combine on the deviation together, because the positive and negative side both has a negative effect on the performance of the problem, I mean, yeah, on the deviation. But if you just combine them, they will cancel themselves, right? So we have to take an absolute value of them, right? So absolute EI, right? Absolute EI, and we going to, yeah, take summation of all these error, some absolute error. So what about this error? EI is the difference between the yi, which is output, real output, right? And we subtract it with axi plus b, okay? Where a and b are our decision variable, and you see that x is only x is our input of our data set, and y is our output of our data set. You see that for in our problem we have 19 points, right? So we have E1 to E19. Okay, so you have to summarize all these things. Yeah, summarize, I mean, sum of the absolute value of the error. All right, so, and in this case we don't have any restriction on the a and b, all right, because a can be positive or negative, a can be positive or negative, right, and b can be both negative and positive. All right, so we don't have any restriction on that. Okay, So I think you can write by yourself, right? I can write some example of this EI, because you have to substitute this equation, this expression, with the real value E1 from the data set given in the table. What is it? Y is 1, right? So it must be subtract by xi. Xi is x1 is 0, so it's 0. I put 0 here and b here, right? And e2 is well, subtraction of the output. Oops, yeah, sorry. Output, our output is 0.9. Yeah, we subtract it with a time with our input is 0.5 plus b, okay? And our E3 is 0.7 subtract with a 1 plus b, okay? You can write other expressions representing E4 to E19 by yourself, okay? So this is the way we formulate our optimization problem in order to minimize the deviation, right? The summation, absolute deviation. Okay. So for the next problem, next question, we want to fit the best straight line where the objective is to minimize the maximum deviation of all the observed value of y from the value predicted by the linear relationship. Of course, our hypothesis is the correlation between the relationship between y and x would be linear, right? But in for the second problem, we don't want to minimize the absolute deviation. We want to minimize the maximum deviation. Okay. So if you remember that from the second class, right? We discussed about this point before, right? So we're going to formulate the minimax optimization problem. Minimax of what? We try to minimize the maximum deviation. Okay. So what are we going to? We want to minimize the maximum. All right. So we want to minimize maximum deviation or maximum error. We don't know what is the maximum error. We can say E star. All right, the E star. Okay. How can we solve this problem? We want to maximize E star, right? So we can say we can say EI, where maximize EI, right? Maximum EI, minimize. And our decision variable again A and B, okay? So what we want to do is we want to minimize, right? We minimize. We assume that the maximum error is E star. So in this case, E star is our maximum error, maximum deviation. And we want to find A and B also E star, because we don't know yet whether, how large is the E star, but we want to minimize that one. E star is the maximum, right? So all we have to do, because we assume that E star is the maximum value, right? Maximum error. So we can say that EI must be less or equal E star, right? Okay, and we want to minimize E star. Then E star is the maximum value. Because E star is the maximum value, so EI cannot be greater than the maximum value. It's just lesser or equal. Okay, and what about E star? E star is absolute value of yi. Subtract by, just one moment, I have to delete this part, right? AXI minus B, okay? Then this one must be less than E star, okay? And you have, well, 19 expression of this. Yeah, very similar this one, all right? You have some absolute of y1 subtract with a x1 subtract with b, all right? Must be lesser or equal E star. All right, and you have, well, absolute of, yeah, y2 subtract by ax2 subtract by b, right? So what else do we need? E star must be greater than 0, because we know that the E star, which is the maximum deviation, must be the, what is it, must be positive, of course. It cannot be negative, so we have to restrict them, restrict this value to be positive only. So I'm going to, well, write some of the expression for you, so later you can see, you can write it down by yourself. We need this one, right? We need this one. It's important, but this one we have 19. Yeah, this one we have 19 of it. So for example, the first one, first point is yi is 1, subtract by a times 0, right? Minus b. This one should be less than E star. And for the second point, we have 0.9 here, right? And then, well, is 0.5 minus subtract by b. And then this is not parenthesis, it must be absolute, okay. E star. You see that I can write down the third point. Third point is 0.7. We subtract it by a, and here it's 1. Yeah, right. Okay, it must be lesser than E star. Okay, you can do it until the last one. The last one is the 19. No, not 10. It's 7.3. 7.3 subtract by a, and our input is 10, right? B, okay. Yeah, E star. Okay, very simple, like that. So you see that, you see the difference, right, between the minimax problem and the, what's it, minimize the summation of deviation. You see that in the first case, we want to adjust, of course, A and B. So we change the slope, yeah, like that, okay. Or we change the B, okay. We change the intercept, all right, in order to minimize summation of the absolute error, absolute deviation, right? Okay. But in the second problem, in this problem, we change A and B, okay. It can be like that or like that, yeah. But our objective is to minimize the maximum deviation, okay. It can be, I don't know, it depends. Well, once you change it, you notice the maximum error, right, maximum deviation, the point which has the maximum deviation, but we want to minimize that one, right? So yeah, this line, we want to find this expression in order to obtain the, what's it, least deviation, okay, from the prediction. Okay, what about the second, the third one, the third, what about the third one? Oh, I think I made some mistake. I explained, but my screen still in the keynote. So, well, let me repeat my explanation again. Of course, yeah. Let me repeat. So, well, for this first problem, we minimize A and B, right? A and B, yeah. Yeah, by adjust A, we adjust the slope, right? And for B, we adjust the intercept, right? So, wow, you see that by adjusting A and B we can represent various relation. But the first problem, you see that we want to minimize summation of deviation. So you change the A and B, right, in order to have a minimum value of the summation of deviation, the absolute value of that deviation. But in the second case, where we derive all the constraint here, right? So well, in this case we want to minimize the maximum error, maximum deviation. So in that case we change A and B, of course, in order to minimize the maximum one. I don't know which one has the maximum value. It depends on the when you change A and B, of course we change A and B, the maximum one we change, right? But we want to find A and B, that the combination of A and B, that well, the maximum error, the maximum deviation is minimum. Okay. What about the third one, the third problem? The third question is we want to fit the base quadratic curve to this to the same data set. All right, so in this case our hypothesis is y is cx squared plus bx plus a. Okay, so we have three parameters now. So you see that we have so we have three parameters. We have c a b c. It's simple. We have a b c as our decision variable. Okay, and what we want, the first one is is analogous to the first problem, but this time the objective function is exactly the same, but the error is the error between the predicted by the not linear model anymore. We find the error or the deviation from the model, which is the quadratic. So we minimize A, B, C again. Have summation of E. Okay, absolute E. That will be better. And what about E? EI is yi subtract by cxi square. Cxi square plus, no, not plus, minus. We have negative. Okay, minus x. Okay, minus a. All right. So, for example, for E1 is the output is 1, right? So you subtract it by 0 square minus b is 0, right? Minus a. And what about E2? E2 is we have 0.9 here, so it's C, and input is 0.5. Yep. Okay. You repeat it until you E19, and E19 is 7.3. C 10 square minus B 10 minus A. Okay. So, and if we repeat using the same strategy as minimax, right? Minimize the maximum deviation. We repeat the same idea. We minimize A, B, C, and E star, and we want to minimize E star, right? So, well, all EI must be, EI is again yi minus c xi. Okay, summation, no, not summation, absolute of that, minus a must be less, absolute, yeah, E star. All right. Okay, so you repeat that, and E star must be greater than or equal 0. Yeah. And well, we can write it this way. For example, 1 minus C square minus V 0 minus A, yeah, lesser than E star. Okay, and the second one, minus C 0.5 square, yeah, V 0.5 minus A, yeah, and lesser than E star. Okay, you repeat it until you get the last one. The last one is 7.3 minus C 10 square, yeah, V 10 minus A, oh yeah, absolute of it, E star. Okay, you repeat all these things. Okay, that's, yeah, it is done for the curve fitting problem. Okay. The next problem is, we call it transshipment problem. So in this problem, imagine that we have several suppliers, and also we have a, what's this, storage, or yeah, or well, if we don't have storage, we can say that, well, we have customer. So the task is to ship some, well, to ship our product from source to customer. Okay, but in some case we can, well, we can ship from supplier to customer first, one customer first, and then later, well, use that customer as transshipment. Then, I mean, well, we ship from supplier to intermediate customer, and then, well, we send through that customer to other customer, something like that. So it's kind of a distribution of material, or distribution of our product through the network. Okay, we have supplier, and then we have customer. Okay, so in this case, consider that we have a case of, well, we have supplier 1, supplier 2, supplier 3, right? S1, S2, S3, and we have customer T1, T2, T3, T4, and it's possible to, well, sometimes to send commodity, right, from one supplier to another before dispatching to another customer. Okay, so we can draw a problem like this, a network like this. For example, we have S1, S2, S3, right? And then, well, from S1 we can, of course, ship to T1, T2, T3, T4, T5, right? For S1, S2 can be sent to customer, and this time S3 we can send to customer 1, 2, 3, 4, 5. Okay, and of course between supplier we can send from S1 to S2 first, and then let S2 to ship the commodity to other place, something like that. We draw all the network like this. And you know that, well, each line, I mean each line, or the shipment from yeah, each direction costs differently. That means, well, for example, if we ship from S1 to S2, it costs 20. If we ship from S1 to S3, it costs 55. And if we ship from S1 to T1, it costs 132. Or we ship from S1 to T3, it costs 97. And to customer 4, it costs 103. Okay, And if we, of course, we know that we can ship between each source, I mean each customer. So well, from S2 we can ship to S1, right? And it costs 35. Okay, and well, you can see the cost for shipment from this table, and the cost is for 1 unit of commodity, unit of product that flow through that direction. And in some direction you see that it costs 0, of course it costs nothing. And in some case, for example, well we have dash here, right? It represents the case that we cannot ship from S1 to S1. Of course it's nonsense, right? We cannot ship the product where the source and sinks are the same. And in some case that we cannot ship the commodity from S3 to S1 because, well, maybe that route is infeasible. Or, well, from S1 we cannot directly ship to customer 2. Okay, you can see from this table. Okay, so our task is, we have to find the minimum cost for all the distribution. So let's set out on this problem. So our objective is to minimize the total cost, right? To minimize the total cost. The cost is the cost for the whole system. And we have to, of course, we have to write the cost as a function of decision variable. So we have to design the decision variable first. Okay, so we have to define our decision variables. Okay, so you see that from the table previously, I previously showed you, we have source and sink, right? We have 3 source, but sometimes, well, source can be synced to source, yeah. For example, S1 can ship to S2, right? And S2 can ship back to S1 too, so it can be treated as source and sink. Also the customer, for customer, in some case, some customer can be treated as source, and also, well, the customer can be sink, right? So we will write, well, we have to design the decision variable first. So we decide to use x to represent the decision variable, and x can be, well, we use ij, yeah, xij. This is good. Xij, where I can be 1 to, we have 3 source, and we have 3 source, right? 3 supplier, and we have 5 customer, so totally 8. Because sometimes, well, source and sink, source can be sink can be source too. And j can be 1 to 8, right? We treat I as source, okay, and j can be sink. Okay, that means, well, for if we write x12, it represents the amount of commodity shipping from S1 to S2. Okay, so that means, well, we use S1 to represent, we use 1 to represent S1, no, to S2, right, to 3 S3, but for 4 it represents customer 1 T1, 5 is T2, 6 is T3, 7 is T4, and 8 represent T5. Okay. So we want to minimize all these costs. Minimize, and we have these variables xij. You know that in some case, for example, x11 is always 0 because we cannot ship through that direction. And now we write the minimum cost, right? So the cost is from the table. We have S1 to S2, the cost is 20, so we 20 of x1 to 2, okay, plus the cost for shipment from S1 to S3 is 45, S1 to 3, plus tier 1, the next one is S1 to T1, the cost is 120, 32. Remember that well, 4 is standing for T1, right? It should be like this, plus the next one is 97, and we have cost, and this is the cost for shipment from S1 to T3. This one is x1 to 6, right? And 103 is the cost for shipment from 1 to T4. S1 to T4. Okay, so we have to write all the costs, right? So we have to, the next line, it's cost for the shipment from x2 to 1, like that. And 85 is the cost for shipment from S2 to T1. T1 is 4. Okay. And the next one is 91 from x2 to T2. T2 is 5. Okay, and you have to sum up all the costs. Okay, you can see from the table that, well, you have any route is possible and it has its own cost per shipment. So, well, we include all those things. Now we look at the constraint. For the first constraint, now we look back to the network again. For the network, you see that for S1, whatever flow from S1, okay, S1, I write S1 first, but remember that for our DC variable, it's I think it's better to say that for example, source from S1 can be shipped to T1, right? So you see this line, the amount of shipment of commodity that ship through S1 to T1, okay, and you sum it up with the amount of the shipment from S1 to T3, S1 to 4, S1 to T5 and S1 to S2, S1 to S3 subtracted by S2 to S1 must be 0 because, well, nothing, yeah, we have to satisfy the material balance here, right? So we can write x x1, right? x1 to 2 plus x1 to 3 plus anything else, x1 to 4, 4 is T1, but no, x1 to 5, we have x1 to 6, the next one, and x from 1 to 7, right? And the last one, let me see the table. Yeah, it's possible. x1 to 8 and then subtracted by x2 to 1, right? Okay, because, well, the commodity can be shipped from S2 back to S1, right? At this node, the material must be 0. Okay, the material balance, yeah, we have to conserve the material balance. And the next one is, yeah, we can look at the second node. Second node is S2. From S2, X2 that ship to 1 plus X2 we send to T1, right? T1 is 4 plus from S2 to T2 S1 cannot be sent to T3 and 3, 4, so we have to consider S2 to T5, yeah. Okay, and then we subtract it by the amount of material that, yeah, then back from S2 back to S1. And it's possible that the shipment from S3 to S2 is possible, so, well, we can say we have to subtract it, yeah. Okay, and this node again must be 0 because no storage there. Okay, of course, well, in some case, if you have storage there, or, well, you know that at that node it's, well, it's that's another flow of material through that node, you have to consider that, yeah, you have to take that into account. So we have to look at each node, and then we have to write down, yeah, we have to formulate the material balance constraint. Yeah, of course it must be equality constraint at that node. Okay, you can complete it by yourself. And, yeah, once we done, we finish all the material balance for each node, then the next constraint should be xij must be greater, must be positive, must be greater or equal 0. Okay, and, well, if you look further at the table, you see that in some direction it's impossible. For example, x1 1 must be 0. You have to write down that, because you know that it's impossible to ship from the same source and sink, right? From S1 cannot be sent to S1. Yeah. Two, 3, 3, 0, 4, 4, 0. Yeah, you can complete that all. Also, look further at the table. You see that from for example, from x1 cannot be sent to t2, so you have to write down x1 5 must be 0. What else? x1 8 must be 0. Yeah, from table. Oh no, not be 0. Yeah, the cost is 0, but that means it's freely. You can ship it freely. But we see from the table. I'm show. Yeah, this from this table. That the dash means impossible to ship the commodity through that direction, through that route. Okay, but 0 means the cost is 0, the shipment is free. Yeah, so you have to include all the impossible pathway, impossible routes to the constraint too, by forcing it to be 0. I mean, the amount of material flow that route is 0. Okay, cost is not 0, but yeah, the cost can be treated as infinity, but we will not treat it this constraint that way. Okay, so we have to write down that the material flow that way is 0. Okay, S2 S3 x from 2 flow to 3 might be 0, something like that. You include all the constraint to the problem, then we can formulate the optimization. Okay, by minimize the cost, right? Minimize the cost here, and we have several constraints, and so on. Okay, so the next problem. This problem is really very similar to transshipment problem. We call it minimum cost flow. For this problem, we have a network, and then of course each network we have several nodes. For example, we have node 0, node 1, node 2, node 3, 4, 5, 6, 7, and we have source, enter, feed into our network through node 0. Yeah, and the amount of the material flow through this node 0 is 10. Okay, plus 10 through this node, and 15 through this node. Okay, and you know that our network has no inventory, so at each time it's similar to the previous problem. Each node, I mean the mass, the material balance must be conserved. So we have to formulate the material balance around each node. Okay, this node, this node, this node, this node. Yeah, and you know that for the whole network we don't have inventory. That means whatever we feed to the system, it must leave the system. It must leave the system here. So the material left the system through node 5 as minus 9, and through node 6 as minus 10, through node 7 as minus 6. Okay, so from this problem, I think you can notice other thing like 5, 4, 2, 4, 6, 5, 6 here. The number here represent the cost per unit of the material flow through this way. You see that is really similar to the previous problem. Okay, now we start working on this problem. Okay, we want to minimize the cost again. Now it's what this minimize the cost. Okay, and we have to write the function of the cost, the cost as a function of our decision variable. So we have to create our decision variable first. The decision variable and the decision variable is xij again. Okay, it represents that the amount xij represent the amount of material flowing from I to j. Okay, so what we have x 0, 2, right? You look at the network, you see that we from the node from node 0 we only have x or 2, right? We don't have x0 1, x0 3, x0 4 because the possible way is just x0 2. Okay, what else do we have? We have, beside that one, we have x02, then we have x1 3. Okay, and for node 2 we have x2 3, we have x24 and x25, x25. Okay, for the flow to node 2 later we will consider. Okay, but now we consider only x23, x24, x25 first. And for node 3 what we have x34 and x37. Four and 7. Okay, and we have at node 3 we have x4 2, x4 5 and 6. For node 5 we have we don't have any material flowing out from node 5. For 6 also only input, no output. And for 7 we have x7 6. Okay, because material can flow from 7 to 6. Okay, so we have to write down the cost then. We minimize 5 of x02, okay, plus 4 x13 plus 2 of x23 plus 4 of x24 plus 5 of x to 5. The next one is x3. x3 we have 1 of x3 4 plus 2 of x3 7. Okay, now x4 we have 6 of x4 2 plus 6 of x4 5. Three of x4 6. Okay, and for x5 no, for x6 no more. For x7, yeah, we have 4 of x7 6. Okay, so we write down on the cost involved in each root. Okay, so what about the constraint? The first one constraint we have, it's xij, or the xij must be positive. Okay, positive means greater than 0 or become 0. The next one is material balance for each node. For node 0, we know that x02 must be 10, right? Because whatever coming through node 0 must leave the system. And for node 2, see that leaving out from node 1, x13 must be 15. Okay, what else for node 2? For node 2, x23 plus x24 plus x25 must equal x02 plus x42. Okay, there are two lines coming to node 2. And for node 3, we have x3 4 plus x3 7, and we have incoming stream from x14 13 plus x23. Okay, well, what about node 4? Node 4 we have x42 leaving the system plus x45 plus x46 and it is x24 plus x34. Okay, for node 5 we have nine is x to 5 plus x45. Okay, and for node 6 we have 10, right, leaving the system and the incoming is x46 plus x76, and for node 7 we have 6 living in the system and x76, this one equals x3 7. Alright, so well we finish all the constraint. Okay, so we finish it, and of course you see that this one, I mean this class of problem is very similar to the previous one, the transshipment problem. Okay, I think that it's not too difficult for you, and in some case, well, it's possible that you have inventory at the you have storage or inventory at each node. Okay, and for that case you have to treat the problem, maybe you have treat the problem as a multi-period optimization problem too. So if you ask me, yeah, it's possible that you combine different category of problems together. For example, you can combine the minimum cost flow and multi-period optimization problem. Yeah, I know you can do it. Okay, so we finish this problem here.